So far in class, we've discussed two of the three standard or basic model systems typically discussed in a quantum chemistry course. The first was the particle in a box. The second was the harmonic oscillator. The third fundamental model system discussed in most quantum chemistry courses, which is the focus of this set of videos, is the rigid rotator, also known as the rigid rotor. We're going to do this in three parts. The first is to describe this rigid rotor system using classical physics. Then, in part 2, we'll carry out a quantum mechanical treatment of the rigid rotor. And in part 3, we'll use the rigid rotor as a model for understanding rotational or microwave spectroscopy. The learning objectives of this video in particular are first to define the rigid rotor model, second to define and evaluate a quantity known as the moment of inertia for a two-body rotating system, and thirdly to define and evaluate another quantity called the angular momentum and understand how we can use angular momentum to define kinetic energy for a two-body rotating system. So the rigid rotor model consists of two masses, labeled here in the figure on the right as M1 and M2. Those masses are at a distance r from one another, and in this model we impose two basic constraints. First, the distance r is fixed, so the two masses don't get to get closer to each other or move further apart from each other. In other words, they're not allowed to vibrate. And secondly, the center of mass is fixed. So no matter how they move, they have to keep their center of mass fixed. In other words, the two-body system cannot undergo overall translation. So the only thing it can do is to rotate about that center of mass. Now our starting point for writing out the physics of the system is to think about the motion and the velocities of these two bodies and to put them in terms of frequencies of the overall rotating system. So the beginning point here is to think conceptually about how these two bodies move as the rigid rotor rotates. Remember, the center of mass is fixed and the distance r is fixed. And so as the overall system rotates, the two masses, M1 and M2, are going to carve out their own independent orbits around the center of mass. And what the diagram from the book shows here is that over a given time, we can think about these two bodies as moving in a plane, or a pseudoplane, or a hyperplane, carving out two concentric circles as their orbits. Now, in reality, the system moves in 3 dimensions, and so over time, what we'll actually see is that the motion of the two bodies maps out two concentric spheres. One with radius r1, describing the motion of mass 1, and one with radius r2, describing the motion of mass 2. But at any given point, we can carve out a hyperplane through that sphere, and we'll see two concentric circles. If we think about how those two bodies move, while the distance traveled by mass 1 and the distance traveled by mass 2 when they each carry out a single orbit will be different, the time it takes for an orbit to be completed, or the time it takes for mass 1 or mass 2 to carve out a pathway that maps completely 2 pi radians around the center of mass, has to be the same as it takes for mass 1. They have to be the same. And so we describe that rate of rotation, or the rotational frequency, by the label nu sub rot, which tells us the number of cycles we carve out per unit time. If we want to describe the motion of the bodies not in terms of complete rotations or orbits, but instead in terms of radians, we can use the symbol omega, which gives us the angular speed. Note that omega, the angular speed, was also used in our description of the harmonic oscillator and had the same definition. It tells us radians per unit time. Now, it may be useful to actually describe the actual velocity in terms of distance per unit time traced out or undergone by mass 1 separately from that of mass 2, and we can do that by relating omega or nu rot, whichever one we have in front of us and want to work with in terms of their radii, and map that back onto a velocity for mass 1, v1, or a velocity of mass 2, v2. Now, I just want to emphasize, these three terms, omega, nu rot, and the v1, v2 terms, can really get people tripped up. So take a little time and think about how they differ from one another and how they relate to one another. Again, v rot just tells me a rate or a frequency of rotation, total rotation. How long does it take me to go all the way around? And we describe that in number of rotations per unit time. Omega, on the other hand, tells me radians per unit time. And V1 and V2 tell me the actual velocity of each body in terms of distance per unit time. So they're all related again, but they are different things. And in order to make sense of the math that comes later, we need to keep straight in our head the difference between nu rot, omega, and V1 and V2. So as we've done in the other model systems, we now want to think about kinetic energy of our system so that eventually when we get to part 2 of this series and we talk about the quantum mechanical system, we can write down a Hamiltonian. So the kinetic energy is just given by the sum of the kinetic energies of mass 1 and mass 2, and those independently are simply given by 1/2 mv squared, and we know how to do that. Now, as we described earlier, it may be that for our system, the physics is better described in terms of the angular velocity or angular speed, or maybe even the rotational frequency. And so we'll want to rewrite the kinetic energy in terms of either omega or nu rot. And the way that your book does this and the way that's conventionally done is to just use omega. So what I'm going to do is to factor out the v squares. I'm going to do some substitutions, and I'm going to rewrite the kinetic energy as 1/2 omega squared times the quantity m1 r1 squared plus m2 r2 squared. Now, as it turns out, m1 r1 squared plus m2 r2 squared has a special name. It's another quantity that we use when we describe rotating systems, and it's known as the moment of inertia, usually denoted by the letter I. And so you can see in the last equation here, the kinetic energy can be rewritten as 1/2 I omega squared. So under the center of mass conditions, and what that means is that m1 r1 equals m2 r2. And again, that comes from our definition of fixing the center of mass of the two rotating centers. The moment of inertia is related to the reduced mass. Same one that we used when we talked about the harmonic oscillator, and so we can rewrite I from being m1 r1 squared plus m2 r2 squared to simply being I equals mu r squared. So again, look what we've done here. We are rapidly moving away from having to talk about the individual distances of the individual bodies from the center of mass to just the distance between the two bodies, r. So we're not using r1 and r2, we're using r. And instead of having individual masses, we'll use the reduced mass, which looks like taking a two-body problem, just like we did in the harmonic oscillator, and turning that into an effective one-body problem, with an effective mass given by the reduced mass mu. Now, if we carry all these manipulations out and we make these different substitutions, and we're effectively trying to move from a two-body problem to an effective or pseudo one-body problem, it also makes sense to think about what the right way to think about momentum of this effective one body is. And the easiest way we have to do that is to think about something called angular momentum. Remember, our system is constantly going around a sphere. And so if we want to describe motion in terms of momenta, we have to think about px and py and pz. And px, py, and pz will be constantly changing as I go around a circle or around a sphere. So it's much easier to think about motion at a fixed distance r from some point in space, going around a circle or a sphere, mapping out or tracing along an angle. So now we can talk about an angle sweep. And the way we think about that, or the symbol we use for that, is L, and we call that thing the angular momentum. And the angular momentum can be related to a product of our angular speed, omega, and the moment of inertia, I. So if we go back to our previous expression of the kinetic energy, which we had given by 1/2 I omega square, we can now replace that expression with one that talks about or relates to a momentum, but in this case the angular momentum, and we get that the kinetic energy is 1/2 times L square over I. So that's where we're going to conclude this first video on the classical rigid rotor system. What we did here was to define what we mean by this model. We described and defined moment of inertia and talked about how it relates a two-body system to a reduced mass with fixed distances between two bodies. We defined angular momentum and showed how it relates to the system's moment of inertia and its rotational frequency or speed. And then lastly, we use the moment of inertia and the angular momentum, which give us good sort of basic ways to think about the motion of an effective one-body system that describes our real two-body system with fixed distance and fixed center of mass, to write down a kinetic energy in terms of angular momentum and moment of inertia. So what we've done here in this summary slide is to outline the 4 key takeaways from this video. First, the general description of the rigid rotor system. 2 new terms that are helpful in our physical description of rotating systems, namely the moment of inertia I and the angular momentum L. And lastly, a new form of kinetic energy that makes use of L and I, 1/2 L square over I. That's it for now. The next video will turn to our quantum mechanical description of the rigid rotor system, and after that, we'll look at ways that the rigid rotor model system helps us describe and understand the rotational spectroscopy of diatomic molecules. I hope everybody's doing well, staying safe, and staying healthy. See y'all soon.